In this video, I want to talk a little bit about injective and get some properties of injectivity kind of here in one location. So remember, a linear transformation L from Rn to Rm is injective if and only if. Okay, I'm going to list a bunch of different properties. Okay, so the first one would be if and only if the equation LV equals W has at most one solution for all W in Rm. Okay, this is kind of like the initial definition that we came up with. LV equals W has at most one solution for every W in Rm. There might be some vectors for which there is no solution, but when there is a solution, there's one. Okay, now this is equivalent, this orange statement is equivalent to the following. If LV1, so V1 and V2 are two vectors, if LV1 is equal to LV2, then V1 is equal to V2. Okay, this is equivalent to saying if LV1 minus LV2 is equal to 0, then V1 minus V2 is equal to 0. All I'm doing is subtracting LV2 from both sides and subtracting V2 from both sides. Using linearity, this is equivalent, so this is equivalent to saying that if, using linearity, this is equivalent to saying that if L applied to the vector V1 minus V2 is equal to 0, then V1 minus V2 is equal to 0. Okay, but now I'm just going to replace V1 minus V2 with a single vector. So if L applied to V is equal to 0, then V is equal to 0. Okay, these are all of these different colored statements, orange, red, purple, blue, and green. These are all different statements that are equivalent to saying that L is injective. Okay, so let's look at some more. So let M equal the matrix V1 through Vn. So this is M sub L. This is the matrix for M. Or sorry, this is the matrix for L. Then another way, an equivalent way of saying that L is injective is to say that M times V equals W has at most one solution. For all W in Rm. Okay, but remember, this is exactly the same as saying the columns of M sub L are linearly independent. Okay, those two statements are the same. That's how we defined what linear independence was to begin with. So these are some ways that the concepts of injectivity, linear independence are related. Let's see if we can get more. Let's see if we can talk about relationships to more concepts. Okay, well, let's think about systems of equations. So let's think about the system of equation MV is equal to W. So we'll think about this system of equations. Well, what does injectivity or linear independence have to do with this? Well, there is a unique solution to this equation. If and only if the columns of M are linearly independent. Okay, so that's how these concepts relate to systems of equations. Okay, so there's a unique solution to this system of equations if and only if the columns of M are linearly independent. And that's the same as saying that the linear transformation defined by LV equals M times V is injective. Okay, so now let's do one of the exercises. In one of the exercises, I asked the following question. Let's say L is a linear transformation from Rn to Rm. Which of the following things do we know? Do we know that is injective? Let me write injective. Do we know that n is less than or equal to m? Do we know that m is less than or equal to n? Or do we know that they're equal? Which one of these things do we know has to be true, if any of them? Okay, well, let's think about this. So we have the matrix. We'll say V1 through Vn. Okay, this is injective, means that the columns are linearly independent. Okay, this means no free variables. When row reduced. So if it's in row echelon form, there's no free variables. So another way of saying that is all columns are pivot columns when it's in row echelon form. Okay, so we know that the number of columns, the number of columns is always going to be greater than or equal to the number of pivots. Okay, when the matrix is in row echelon form, the number of columns is always greater than or equal to the number of pivots. Why is that? Because there's going to be at most one pivot per column. Okay, so the number of pivots is always less than or equal to the number of columns. If there's more columns than the number of pivots, that means there's free variables. But there are no free variables, so it means that the number of columns is equal to the number of pivots. And similarly, a matrix, no matter what form is in, the number of pivots is always less than or equal to the number of rows. Because remember, a pivot is the first non-zero entry in each row. Okay, so the number of pivots is less than or equal to the number of rows. Okay, so overall, this equality, or this inequality, says the number of columns is less than or equal to the number of rows. But there are n columns and there are m rows. Okay, so overall, this says that n is less than or equal to m. Okay, so it'd be this equation right there. So n is less than or equal to m. So if a matrix is injective, then if a linear transformation going from Rn to Rm is injective, then n has to be less than or equal to m. Okay, how can we relate this to some other things? Well, similarly, we saw that if a set of vectors v1 through vn is linearly independent, then n has to be less than or equal to m if the v vectors are in Rn. Okay, so this is how we relate this to linear independence. And what about systems of equations? Well, let's say we have a system given by the matrix vector equation mv is equal to w. If m is an m by n matrix, then there are m equations in n unknowns. Okay, and so to say that mv equals w either has 0 or 1 solution for every w in Rm is to say that m is overdetermined. Okay, that would be one way, that's like sort of the intuitive way to think about this. But if m is overdetermined, that means there's more equations than variables, which means that m is greater than or equal to n. So again, that illustrates this idea that linear independence, injectivity, system uniqueness of solutions to systems of equations, they're all just different ways of talking about the same thing. And this thing with the m being greater than or equal to n is just one way to kind of illustrate that. It's one manifestation of that. That injectivity, linear independence, uniqueness of solutions all kind of go together in one ball, and to really kind of I'm urging you to kind of think through this and understand why all of these things relate to each other and how they all relate to each other.